Part 2 of Chapter 6, or Section 2 of Chapter 6, I'm going to talk about molecular compounds and ionic compounds. Just a little bit of a review. You should remember that in molecular compounds, electrons are shared, and molecular compounds form between two non-metals. Alright, let's talk about the energy of bond formation, because in molecular compounds we actually have chemical bonds forming. Alright, the potential energy, or the energy that is possible within that bond, is based on the position of an object. If a bond has low potential energy, then it has a high stability. Okay. What is bond energy? Bond energy is the amount of energy that is required to break that bond. So a lower potential energy increases stability. Let's talk a little bit about bond energy and bond length. If you have a shorter bond, meaning the radius of your atoms that are bonded together are smaller, so the smaller the atom, the smaller the bond length, the higher the bond energy. So the shorter the bond length, the higher the bond energy. That's why you have a lot of bond energy in hydrogen-to-hydrogen bonds. And I've showed you videos of where hydrogen has been exploded, and it has just an amazing amount of energy that is held within those bonds. Let's talk about Lewis structures. You should remember Lewis structures from physical science, maybe in middle school. And Lewis structures are a very nice way of showing the bonding electrons in atoms. Now, electron dot diagrams. Each dot is a valence electron. Okay, so show valence electrons as dots. X being the general formula or the chemical symbol, and the dots meaning the valence electrons. Remember, the octet rule, everything wants to have 8, or everything has 8 in its outer valence. You distribute the dots like arrows in an orbital diagram. If you remember orbital diagrams, we have 4 sides on each of our chemical symbols, and each of those 4 sides stands for an orbital orientation. You should remember that we have one s orbital. It's a spherical shape. We have 3 p orbitals, and those are the dumbbell-shaped orbitals, and they sit along the x, y, and z axes. Now we have a very particular way we want to fill these, so let's practice with oxygen. Okay, here's the electron configuration for oxygen. We have 2 electrons in our s orbital. So first of all, when we start off with our dot diagram, we're going to start off with our chemical symbol. Chemical symbol for oxygen is, of course, O. And we're going to fill in a very particular manner. Alright, the top is our 2 s orbitals. Alright, and we can go next to our next side, bottom side, the other side. And remember, Hund's rule tells us that we cannot pair up an electron until every other energy level has been full. So this is how we have our oxygen dot diagram. You have 2 electrons paired up and then 2 lone electrons on either side of the oxygen. Remember, every energy level must be full before you can pair anyone up. So if this electron was over here, it would not be correct because we would have an energy level that did not have something in it. Okay, the octet rule. You should remember that the octet rule says that most atoms want to form bonds in order to obtain 8 valence electrons. Okay? And it wants to achieve a full energy level stability, like the noble gases. Remember, all of the noble gases have 8 electrons in their valence shell. It wants to be exactly like a noble gas, so it can be stable. Alright, let's look at this example. We've got 2 chlorine atoms that are going to form a molecular bond. They're going to bond together. Now, they each have 7. What they can do is they can share this extra electron they have in each of these energy levels and share these 2 electrons, so that way they both have 8 in their valence. Let's look at another example, water. It's a little bit weird because hydrogen only wants 2 in its valence shell in order for it to be happy. So what it can do is it will pair up. One of the hydrogens can go to one of the hydrogens is going to bond to one of the electrons in the oxygen, and another hydrogen is going to bond with the other lone electron in the oxygen atom, and you end up with a structure like this. Remember, hydrogen and helium are both a little bit weird in that they don't want 8 in their valence electron. They're perfectly fine with 2. Remember, in polar covalent compounds, we have no charges because electrons are being shared. We're not gaining or losing electrons. But you should remember we have partial charges in polar covalent compounds, and we have to label those with the delta negatives and delta positives. How do we do that? We look at the electronegativity chart that you have received. All right, let's talk about ionic compounds. Remember, ionic compounds lose or gain electrons, and it forms between metals and nonmetals. Metals lose electrons to become positive. Nonmetals gain electrons to become negative. And the energy that we're talking about, or the energy of bond formation in ionic compounds, comes from the lattice energy. And the lattice energy is that energy that is released when a mole of that compound is formed from the gaseous ion, or the amount of energy released when it is formed. You've got some lattice energy examples right here. Not that important yet. We will get to thermodynamics and kinetics a little bit later in the year. Lewis structures for ionic compounds. Remember, ionic compounds lose or gain electrons. So we're going to see not a sharing of electrons like we saw in the molecular compounds, but electrons are actually going to leave or come to the ionic compounds. Remember, covalent share, ionic transfers or moves. So for example, sodium and chlorine. Now, sodium wants to lose an electron so it can look like its next lowest noble gas, and chlorine wants to gain that electron so it can have 8 in its outer shell. Okay, so how are we going to do that? We can transfer these electrons. When we transfer, when we take this negative piece and give it to chlorine, sodium is going to be losing negative piece, so it will become positive. Remember, we're going to transfer that electron. It's going to become positive, and then chlorine is going to gain that electron and become negative overall. And that is it, ladies and gentlemen, for Chapter 6, Part 2.